Hi, I'm Mike, and this is our work on variational item response theory. It's a collaboration with Rich, Ben, Chris, and Noah, who are all at Stanford. So for some motivation, we're working in measurement science, which means we want to estimate some ability based on people's responses to questions. So for example, standardized exams like SAT want to gauge student understanding based on responses to multiple choice questions. And similarly, surveys want to do the same thing, but for your preferences to different products and websites. And even in medical diagnostics like the eye exam, you're being asked a series of questions to try to gauge your visual acuity. So in an ideal world, this is an easy problem because we're asking perfect questions and people are answering each question perfectly, which means that we can just pose any question and get a perfect estimate of each person's ability. But what makes this difficult in the real world is that our questions are imprecise and there's a lot of noise surrounding people's responses. So for example, when you take an SAT test, just because you got one question wrong doesn't mean you don't understand that concept. You could have just misread the question. For some other motivation, in recent years, we've seen that datasets are getting bigger and bigger. And these bigger datasets pose new challenges and opportunities in measurement theory. So on one hand, bigger datasets can give us the power to fit more expressive models that are more accurate. And this accuracy can lead to better understanding of human behavior. But on the other hand, bigger datasets can cause technical difficulties. The classic algorithms that we like may no longer be optimal or tractable, and we may face nasty trade-offs between speed and accuracy. So one of the main challenges in this work is to see how we can leverage large datasets to better estimate ability from noisy responses. So let's first think about the classic way to do this, which is item response theory, or IRT. And let's focus on the exam setting where we're measuring student ability. So the IRT model is very intuitive. It just says that the probability that a student gets a particular question correct is a linear function of that student's ability and the item's difficulty. So thinking about this a bit more, that means that the higher your ability is, the more likely you are to answer a question correctly. But the harder a question is, the less likely you are. So we plotted the IRT function on the right here, and you can see the x-axis is ability minus difficulty. So if your ability is bigger than difficulty, you have at least a 0.5 probability of getting this answer correct. Now, there's a variant of the IRT model called the 2PL IRT model, which adds a slope parameter or discrimination parameter per item. And what this slope parameter does is measure how good each question is at differentiating students. So imagine that some questions are really good at teasing apart very high ability students with moderately high ability students, whereas other questions are not. So graphically, what this translates to is that it changes the shape of the sigmoid function. Okay, so what we often want to do with IRT is to do inference. So we're given a data set of n students responding to m items, and we know if each one is correct or not. And so what we want to do is infer the ability for each of the students and the item difficulty and slope for each of the questions. And there are many ways to do this, and we'll just go over two briefly. But the most straightforward way is maximum likelihood. So given some data set of observations of all the responses that students make, let's just pick the most probable ability and item difficulty and slope that could have led to this data set. So the primary benefit of this approach is that in general, inference is a very hard problem, but here we've reduced it to a linear classification problem, like logistic regression, which is shown in the figure on the right. So here we have two groups. Let's say one group is students who can answer question A correctly, and one group is students who can answer question A incorrectly. And what we're trying to do is find the weights, which here means ability, difficulty, and slope, that best leads to a linear separation between the two groups. And because we know how to do logistic regression very well, this is cheap and easy to do. But the consequence of maximum likelihood is that it's just a point estimate. So you have no way of characterizing how confident or uncertain you are about your inferred ability, difficulty, and slope. And we'll see in our experiments that this could lead to poor performance. So on the other end of the scale, we have Bayesian methods. And here, we don't just do a point estimate. We use Bayes' rule to try to derive a form for the true posterior distribution over ability and item features. But this true posterior is kind of unwieldy. So often we have to use sampling methods like MCMC or HMC to sample from it. And with enough samples, we can get a distribution, an empirical distribution that we can use to estimate variance. So the primary benefit of this approach is that from a statistical point of view, it's in some sense the right thing to do. And in particular, capturing variance turns out to be very important. So as an example, if you have some bimodal distribution for the posterior overability, your point estimate might only focus on one of the two peaks, which sort of ignores an entire half of the distribution. However, the consequences of this approach are kind of outweigh the benefits. In particular, it's really computationally expensive. So doing MCMC does not scale well as the dataset size grows and quickly becomes intractable. Thus, this is not that popular of an approach in industry and research. So what we're kind of looking for is to get the best of both worlds. Can we come up with a new inference algorithm that can capture uncertainty like MCMC can, but also be as fast and cheap as maximum likelihood? And what our paper shows is that we introduce a new estimator called VIBO. And so to explain how VIBO works, we'll give you a quick crash course in variational inference. So here, we're still interested in the posterior distribution, but we don't want to sample from it because that's too hard. So instead, let's pick a family of distributions capital Q. For example, this could be all the Gaussians in the world. Now, let's pick a distribution Q inside this family such that Q is approximately equal to the true posterior P. And how we measure equal is using a distance function between distributions, for example, KL divergence. So we want to pick Q such that it minimizes the distance between itself and the true posterior P. Graphically, we can visualize this like this. So you have some gray blob here that represents the posterior distribution, and you have the orange distribution that represents your variational distribution, or the Q that you picked inside your family. So early in optimization, these two distributions will be very different, but as you continue to optimize, you're going to find the Q that's most similar to the posterior inside your family. So in summary, the benefit of variational inference is that it again casts inference as an optimization problem. So this is similar to maximum likelihood, but here we don't just have a point estimate. We have an entire distribution Q that we can use to measure uncertainty. Okay, so that's all VIBO is. And recent advances in deep generative models and machine learning have made it easy for us to do this particular kind of optimization. So now let's see what VIBO can do. We start with some synthetic experiments, which means that we randomly initialize some 2PL IRT model. So we randomly pick abilities and item difficulties and slope. Now using that IRT model, we sample data. So we sample a matrix of n students by m items. And what we want to do now is compare different inference algorithms like VIBO to maximum likelihood to MCMC and to EM, or expectation maximization, which is another popular point estimate method used in industry. So here we also want to stress test each algorithm a little bit. So we vary the number of students in each data set from 100 to 1.5 million, and the number of items from 10 to thousands. And for each of these settings, what we measure is how fast each algorithm is based on just runtime, and how good each algorithm is. So to get a sense of this, we can measure the correlation between the inferred ability and the true ability, which we know because we generated this data set. But we can also measure something we call missing data imputation, which means we take our generated matrix and we randomly mask out 10% of the responses. And we only use the remaining 90% to do inference. So the question is, how well can each algorithm fill in the missing 10%? And unlike correlation, this measures a sense of overfitting. So you might imagine that some inference algorithms do really well for responses that they observe, but cannot generalize to pairs of persons and items that they did not see in the first step. Okay, so let's look at some plots. So here we show three subplots comparing time costs as we vary different things. So on the left, we vary the number of people, and then the number of items, and then the number of dimensions. And in dark blue, we have VIBO, and in pink, we have maximum likelihood, and in orange, we have HMC or MCMC. So some patterns to note are that VIBO is only slightly slower than maximum likelihood, which is a really good sign because training a logistic regression model is about as fast as we can get. And VBO is actually orders of magnitudes faster than MCMC, even though both are fully Bayesian approaches. So in particular, for 1.5 million students, MCMC takes 217 hours, whereas VBO takes 800 seconds. For 6,000 items, MCMC takes 4.3 hours, whereas VBO takes a little less than 400 seconds. So these differences are massive. Second, now we can look at how good inference is. And here we plot the same three subplots, except on the y-axis we plot correlation between the true and inferred ability. The first thing to note is that performance is generally good across the different algorithms. So for persons above 500 and items above 50, the correlation approach is 1, which is perfect. But there's an exception. So VBO doesn't seem to work very well with very few people, like 100, and very few items, like 10. So what we'd recommend is that if you have a small data set, you should just use classical methods like MCMC, which is tractable there. But once it becomes untractable, VBO is a good alternative. And finally, we can also look at missing data imputation. And the same patterns kind of apply with two exceptions. First is that MCMC and VBO have far better missing data imputation accuracy than other methods. So if you look at the first subplot on the left, you can see that the dark blue and the orange lines are much above the other lines for people above 500. And in particular, this implies that maximum likelihood and EM aren't as good because they overfit to the observed data. And this is some evidence of why capturing variance is important. It helps you do inference well for examples that you haven't seen as well, resulting in better missing data imputation. Okay, so we have some sense of some promising results in the synthetic setting, and here now we consider real-world data sets. And in total, we explored 5 data sets, 3 of which are surrounding language acquisition. So here you might have English speakers who are answering questions to a grammar or syntax quiz, or you might have people using an app like Duolingo who have to choose the correct word from a set. The remaining 2 data sets are more classic exam data sets. So the first one is from Gradescope that tracks assignment scores throughout the span of a course. And the second is PISA, which is this large high school international standard exam. So if we look at the size of these data sets a little bit, you can see that the first critical language acquisition data set and PISA are very large, 500,000 students and above. So let's look at some similar results to what we looked at in the synthetic case. So for each of these subplots in the x-axis, we plot the missing data imputation accuracy. And on the y-axis, we plot the amount of time in seconds saved versus using MCMC. So that means what we want to be is in the upper right-hand corner, because those are the efficient and effective inference algorithms. So the purple square is VBO, the green diamond is MLE, and the blue circles is MCMC. So the blue circle should always be on the x-axis because you can't save any time comparing to yourself. But what we already noticed is that the purple square, or VBO, is always the most in the upper right-hand corner. And in particular, we can find similar patterns as we did in synthetic examples. So VBO outperforms MLE and EM in missing data imputation by up to 8% across these data sets, which suggests that, the latter 2 point estimate methods suffer from some overfitting, but also that MCMC on the language acquisition or the PISA dataset would take 120 hours, whereas VBO would only take 50 minutes to 5 hours. Okay, just to summarize, we were looking for an inference algorithm that could share the benefits of 2 worlds, right? As fast as MLE, but able to capture uncertainty like MCMC. And we introduced such a new inference algorithm called VBO. And you can find our implementation online, and we're working to release a pip package that can be easy to use like MERT. Thank you so much.